All right, let's do some applications of specific heat. All right, particularly this problem will be taking two substances to thermal equilibrium and calculating the final temperature. Share your screen. Share. Okay, make sure you have a calculator. This is a bit math heavy. But first, let us discuss this concept of thermal equilibrium. Okay, and that's nothing more than when you have two objects at different temperatures. Let's say when two objects at different temps, you want to envision one hot and one cold. When those two objects come together, heat is exchanged. Until both arrive at the same final temp, right? And what you need to realize is that the heat lost by the hot object will be equal to the heat gained by the cooler object, right? The temperature change will not be the same, but the heat exchange will. Therefore, let me move this down a bit. Therefore, heat loss would be symbolized by negative Q. Heat gained is symbolized by positive Q. They are equal to each other. The heat lost is equal to mc delta T. The heat gained is equal to mc delta T, and those two are equal to each other. So here is our equation, and we will actually have to solve for the final temperature. All right, it just requires a lot of algebra and not making stupid mistakes. So let's look at what's going on. We've got a piece of iron. So we'll draw that piece of iron right here, and we're going to find out that it is hot, okay? We in fact have the mass of iron is, hold on, oops. The mass of the iron is 21.5 grams, and it is at a temp initial that is 100.0 degrees Celsius, and we are later told that the specific heat of the iron is equal to 0.449 kilojoules per kilogram Kelvin. I'm telling you that that is the same as 0.449 joule per gram degrees Celsius. That is legit. I could prove it, okay? All right. We also have over here a cup of water, insulated, assuming that's to make us think that the heat is not being lost to the surroundings. So it's an assumption. The mass of the water in the cup is 132.0 grams. The initial temp of the water in the cup is 20 degrees Celsius, and the specific heat of water is 4.184 joules per gram degrees Celsius. And we need to know what is the final temp, right? And we know that they will both come to thermal equilibrium, right? Picture this, the hot iron goes into the water and heat will be lost to water, right? So Q per Fe will be negative. The water is gaining the heat. Water, I'm sorry, I didn't want to write that. I'm going to write heat gained from iron, right? It's all about heat exchange, and that is a positive Q. And these Qs are equal in magnitude, right? But opposite in charge. So we've got MC delta T for the metal equals, oops, goodness gracious, equals MC delta T for the water. Okay? The mass of the metal is 21.5 grams. The specific heat is 0.449 joules per gram degrees Celsius. The change in temperature is the T final minus the initial, which is 100.0. We are solving for T final. We will call it X. Yeah, we'll call it, no, let's just leave it T final. It's equal to the mass of the water, which is 132 grams. The specific heat of the water, 4.184 joules per gram degrees Celsius. And the change in temp of the water, okay? That is always the final. So we're solving for minus the initial. All right? So we just plugged in our data. Now we've got to do the algebra. And first step is to start simplifying. So I will multiply this by this, and I will multiply this by this, right? Start bringing some like terms together. We are solving for the final temperature. So I may call that X from now on. So let's do 21.5 times 0.449. It's going to give us, let me get my green back. It's going to give us 9.6535. Grams cancel, joules per degree Celsius. All right. I'm then going to multiply, let's just write it all down, TF minus 100 degrees Celsius. I'm going to do this one, 132 times 4.184. It's going to give me 5.5 to 2.88 times 10 to the second. Grams are gone, joules degrees Celsius times final temperature minus 20. I did not change it to X. Okay, I will now distribute again, this times this minus this times this. And I will do the same over here, this times this minus this times this. I'll set them equal to each other. So in my calculator, I've got 9.6535 times TF. Let me just write that, 9.6535 joules degrees Celsius. I'm going to go ahead and call F TFX, okay? Minus 100. Oh, hold on. Let's go ahead and actually calculate. Let's do 965 times 100, and we'll minus that. It's going to be 965.35. Our degrees Celsius there will cancel when we multiply them, and that's joules. Equal to, let's do 5.52288 times 10 to the second joules degrees Celsius X, remember we called TFX, minus, now I need to multiply the 5.52288 second E to times 20, and that gives me 1.10456 times 10 to the fourth, and that is joules because my degrees Celsius just canceled. Now I will combine like terms. So I'm going to subtract this X from this X. All right, that's going to give me a 0. This is going to give me 9.635. Oops, 35. I wrote that down backwards, right? Right here it says 3.5, 9.635 minus 5.52288 second E2 equals, that is negative 5.42653 times 10 to the second joules degrees Celsius. X, I'm continuing, right? That's this. I need to add this to the other side, right? That's 0. And this will go right here. Here's our equals, right? So it's plus 0 equals minus, so I've got 1.104576 second E2 plus 965 point, oh, that's an exponent of a 4, guys. 4 plus 965.35 equals, I've got 1.2011 times 10 to the 4th, and those are joules. Okay, those are joules. All right, so essentially here, doing this the hard way, showing all the steps, it would be easier to probably not, oh, there's my X, I just lost my X. X, remember that's my TF, equals negative 1.2011 times 10 to the 4th joules. Let's solve for X by dividing both sides, right? Getting him to the other side. So dividing both sides by negative 5.42653 times 10 to the second joules. And what I get divided by is X, that's joules degrees Celsius, cancels. I'm left with degrees Celsius, beautiful, and I've got 22.1. So the final temperature here is 22.1 degrees Celsius. Makes sense because the water was at 20, and when we put the hot metal into it, it went to 22.1. Notice the water heated up a little bit, but look at that metal. It went from 100 all the way to 22.1. So what does that tell us? That tells us that our metal has a much lower specific heat, as the temperature changes much more easily than does the water, right? So we cannot relate changes in temps, but we can relate directly compare specific heats. Okay, good job, good job. Next problem will be in the next video. Okay, so.